over one day. We also have only in the department, the event is a Taiwan recruitment event. Okay, there will be talks in the afternoon, okay, after 2 at the Audi 2. If you guys are free, please join. If you guys are not at the career fair, yes, I am also a part of the career fair. Please go there also. All right. We have the whole thing, a career thing tomorrow. Okay. So career minded, all career things. All right. So yeah. Okay, enough of tomorrow. Okay. So today it is today. Okay. Vika, give a truth table for half adder. So half adder. So half adder, you have your 2 inputs, and then you've got a sum and a carry out. Okay. So you've got 2 inputs. Therefore, you have 4 possibilities. Okay. So this is the truth adder for a truth table for a half adder. Okay. 2 inputs, and then you have a sum and a C out. So how's the circuit could look like? Okay, so you just find the SOP of the C out and sum. You have your circuit. Okay, this is a very simple circuit. Okay, that makes up for the XOR and an AND. Now, full adder using half adders and minimum number of external gates. So, in order to build a full adder using half adder, you need 2 half adders, right? Okay, in order to build a full adder using half adders, you need basically 2 half adders to build it. Okay, so remember that. Okay, so again, you have the sum and C out and the output. So this is a block diagram of the full adder made up of 2 half adders. We call it as a decomposed full adder or a modular full adder. Okay, this is a question. A full adder can be implemented using basic gates in many ways. Okay, I need to bring you to the last slide. I hope it's here. Lecture. Maybe it's a download. Last week's lecture we did mostly on adders, right? Okay, this was last week's lecture, whereby I showed you the expression for full adder, right? So if I go back to this lecture notes, okay, go back to the slide where I introduced to you guys the full adder expression. Okay, you have the sum and the C out, right? Okay, so if you would look at here, you've got, for the full adder, you've got 3 inputs, yeah, two inputs and a Cin, of course, okay, 2 inputs and a Cin. And then you have your output at the sum and the C out. So you've got C sum, which is the input XORed, okay, so the inputs are X, Y, Z, C. So C as in the carry in, so X XORed with Y, XORed with C. And the carry out equation is, the expression is xy, the input x ended with y, or with x ended with cn, or with y ended with cn. Okay, so this is the carry out, okay, for a full adder. And then we even went to the point where we named the cn. If you would remember, the cn we separated into propagation and generation, P and G, right? Here, okay. See, again, this is the full adder just now, the circuitry, okay, and the KMAT, and I said the sum expression and the CR expression, and we even call this as G, the generation, and this X ORed with Y as the propagation. Okay, from this full adder, we build a carry look ahead adder. Alright, okay, bear this in mind. Okay, bear that in mind. Go back to the question here. Now what I want to do is, I want to implement the full adder using the least, well, a small number of gates. Okay, a small number of gates. Here is my full adder, which I showed you before. I've got 1 XOR, 3 AND, and 1 OR. Okay, this is from this sum. Sum is using the XOR, and the carry out is using 3 AND gates, and one OR gate. Okay, so what I want to tell you guys that, okay, for this sum, okay, it's possible that we can just use this XOR, but for the carry out, there's another way to do it. Okay, for the carry out, instead of using 3 AND gates and 1 OR gate, what we can do is we can use instead this one. Okay, I'm looking for my pen. Alright, if you look at this one, right? I have this set to carry out, right? It's xi plus xicn plus or yicn. Okay, this is what we found just now. And we can make it into xyiy plus cn xi plus yi. Xi or with yi. Okay. And there's another way to do it in such that instead of having this and, okay, you can use instead an or gate. Okay? XOR, sorry. Instead of having an OR gate, we use an XOR gate. Okay? That's another way to do it. It is logically the same, logically identical. When I say logically identical, if I'm going to use this XOR method instead of this OR method, okay, the result is the same. The result is the same. So here, say we have two input, A, B, and C. C is the third input. Okay, A, B, and C are the inputs. Say I want to find the AB, which is the XY. Okay, here in my slide is AB. So AB. Okay, so AB is this. Okay, this column here. Okay, and if I were to find A XOR with B, okay, which is XI XOR with YI, so that is the green, here is the column. And then if I were to find the C out is AB OR with C in, or ANDed with the A XOR B, okay, which is this one which I showed you just now. Okay, instead of here having an AND gate, I'm using an XOR gate. Because remember last week I did say XOR gate is very useful. So usually people would prefer to use XOR as compared to an AND. Okay, so as compared to the OR. So here I'm changing this OR expression into an XOR expression. Okay, it's logically the same, but if you were to use Boolean, it doesn't work. Okay, if you use Boolean expression, Boolean manipulation, it just doesn't come to this equation here. But logically, as I showed you here in this table, it can come up with the same output. Okay, so here if I find the XOR, if I find the C out using the XOR method, I've got this input, this output here. Okay, if I were to use this the normal method, which is this expression here, okay, I find the AB ORed with AC in, ORed with BC in, I have this C out, okay, which is the same, okay, which is the same. So other books, they are books, okay, if you find books, they show that they're using this expression here. This expression is quite straightforward, whereby we found this expression from the KMAT, okay, from the KMAT here, okay, which I showed you last week, okay. But I'm just telling you guys that there's another way to implement a full adder in which you can replace this OR expression, this XOR term, into an XOR term. Okay, so you've got AB ORed with C in, ANDed with this XOR expression. Okay, so by having that, what I'm having is, I'm lessening the number of gates. Instead of having 3 AND gates and 1 OR and 1 XOR, I would only just need 1 XOR, 2 XOR, 2 AND, and 1 OR. Basically, I've got a total of 5 gate delays as compared to a total of, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5, yeah, 1, 4, 5, okay, yeah. In terms of the number of gates, it's the same, but in terms of the way it propagates, okay, it's more faster, okay. You have this parallelism to be able, okay, parallelism, and as in, if you remember carry lookup adder, it's more as opposed to the ripple carry adder. Ripple carry adder, it has delays because it takes time to propagate, right, from one block to the other. And then we learned about carry look ahead adder, in which the adding, the summation is done in parallelism mechanism. It's parallelism technique. Okay, so same thing here. If you use XOR, you can enable that parallelism technique to be done. Okay, so parallelism or faster, okay, method can be used using XOR as compared to using the OR method. Okay, but I'm just telling you guys, just sharing. There's no wrong if you use this method using the OR method. There isn't anything wrong as well if you use this method as well. So there are many ways to design your full adder. Okay, so here I'm just showing you that. Okay, another question. Now I'm having a 4-bit carry look ahead adder using the following definitions. Okay, I'm giving you the definitions now. Now the generate is GI equals A ANDed with B. Propagate is PI whereby A, I, XOR to B. Now be aware that where do I get this? I get it from here. If you would remember, G is my generate, P is my propagate. In the last lecture, I gave this, I'm using this one. Okay, I'm using this one in the last lecture. Now I'm showing you guys that I'm using this one as my propagate. Again, there's no wrong in doing so because I've showed you that if I use an XOR, it gives the same logical output as the OR. So it's fine. So here, on the lecture notes of last week, I'm using P, propagate, as XOR with Y. But for today, I'm using the P in which XOR P equals A XOR B. Okay, P equals A XOR B. Propagate. The word propagate also, like if you would remember, what is the truth table for OR? Okay, say if I say this is the Y, right? The output. Okay. So 0 0 0 1 1 0 1 1. Okay. So if I use OR, okay, if this is an OR, okay, 0 0 1 1 1, right? This is an OR. If I use XOR, 0 0 0 1 1 0 1 1. Okay. Okay. So if this is an XOR, okay, so it's 0 1 1 0. Okay. So if I were to just use the definition of propagate is just the definition of propagate is to just bring the bit from one block to the other. Propagation. But here, this XOR, in terms of the definition of propagation, it meets the criteria, meaning it's just propagating the bit out. Okay, but if I were to use OR, just looking at the definition, so they say at this 1-1 combination, it generates a 1. They call it, they generate a 1. So if I were to look at it in terms of definition alone, OR is not really a good, gate to use as a propagate, as a P. Okay, as compared to an XOR. So usually that is why people they settle with using an XOR as a propagate as compared to an AND, as compared to the OR as the propagate signal. Okay, so just to share with you guys, but there isn't anything wrong if you use the OR. Okay, because logically it gives the same output. Right. Okay, so looking at this question, I'm giving already the propagate. Okay. Propagate is PI Okay, PI A XOR with B. The carry out for PI is given. Alright. C1 is here, C2, C3, and C4, which is the C out. Okay, so you're given, how do I get this? If you would remember last week, we showed you how to get one point to the other, okay? One line to the other. Go back to the lecture slide of last week under CLA, okay? I even give you an example of the CLA of last week's lecture. Okay, first question. Explain the advantage of a carry located adder or CLA as opposed to the RCA or triple carry adder in terms of speed and performance. Okay, that's question A. Is this a test question? Yeah, I don't know. For question for question B, for input A 1011 and B 0110 and C compute G and P, which is already given here. Okay. And the carry bits C1 to C4 using the CLA logic, which is this one, okay, using these statements here. And then question 3, based on your computed values, determine the sum. Okay, alright, easy enough because you're given this, right? So you just have to use these in order to find B and C. Let's look at A first, okay? So just to give you a feel, alright, for exams or tests, this is what you would get, okay? If a question comes up, you will not just be calculation, okay? I'll be asking some questions like this as well, some explanation, some things maybe you have to draw, okay? So now A, explain the advantage of using CLA as opposed to RCA or ripple carry adder in terms of speed and performance. Okay? So ripple carry adder completes each bit sequentially, meaning delays accumulate every bit. Okay, so there are delays from one block to the other when it propagates along. Okay, so that is the disadvantage of a ripple carry adder. Okay? For carry look adder, it works in parallel. You've got parallelism. Okay, so it computes all carry bits in parallel using generate and propagate logic. Okay, if you look at this one, it calculates all C1, C2, C3, C4 at once. Okay, but for ripple carry adder, you have to bring the bit from one block to the other. One block, one is settled, one is done computation, it goes to the next block. One is done computation, it goes to the next block. So that is the disadvantage of the ripple carry adder. Alright, so basically CLA reduces the overall propagation delay, increases the speed, especially for wider adders. If you've got wide, long bits, okay, you wouldn't want to be burdened with the RCA. So that CLA is faster, more efficient in large digital systems. Alright, but in terms of its complexity, of course, complexity-wise, CLA is more complex, the schematic, okay? With a lot of wires, okay? But ripple carry adder is more simpler, okay? But if you have a wide adder, a lot of bits, n equals 32, for instance, here, you would not want to use the RCA, you would prefer to use CLA. Now, for the computation now, you're given A and B and C in, find G and P, so you're given already, okay? It will always be like this, okay? G is here, this is the one that I gave you lastly. This is G, right? This is G. G is always A times B. A added with the X, the input, added with the Y, the input, okay? So G is always like that. And I said P, you can either use the XOR or the OR function, alright? Okay, going back here. But in the question here, it gives you the XOR function, so you use that. Okay, so you have defined your propagate and your generate symbol. Then you find the C out. You use this one by one, C1, C2, C3, C4. Okay? Right. Now C, based on the computed values, determine the following sum. Find the sum. Okay, so just A and yeah. Okay, so the sum is the G actually. Okay, so sum is not the G. Sum is PI. Basically, what is sum? This one. X XORed with Y, XORed with C. Okay, this one. This is sum. This is sum. S here. This is sum. Alright? Your input XORed with your C in. Carry in. Okay, since you already have your P to be an XOR, Okay, remember your P here, if you choose P to be an XOR, you can just include it as your sum operation. So P XOR with Cn. So that is your sum. Okay, guys? Alright. Okay, so that is your sum with a carry out of 1. Okay, if you add all this up, you get a carry out of 1, which you got for the C4 is 1. C4 is your carry out. This is C4. Okay, I do not want at the end of like week 14, you ask me this question again. Okay, because I forget. Okay, so if you have any question, you ask now. Alright? Okay, no talking please. Alright, I can still hear your sweet voices. Alright, thank you. Alright, introduction. That was just a wake up exercise. Okay, so level of abstraction. This is basically what you're learning in digital design, right? First, well, in your EE journey, right? You've learned about electronic physics, you've learned about the electronic circuits. Now you are here, digital systems, now you're digital design. Later on, if you want to go VLSI, and so on. Embedded systems in your fourth year as your elective, this is what you will learn. Alright. So combinational circuits are stateless. It's not like the sequential, right? Okay, it's stateless, but it's dependent only on its input. Okay, so these are your blocks, your common combinational blocks. Okay, again, there are some things that you guys learned in your first year, but it's good to refresh. Okay, and something new as well. Okay, so one by one, multiplexers. This is your circuit for multiplexer. 2-to-1 multiplexer. Please remember. Okay, multiplexer. It comes up with 2 AND gates and 1 OR gate and with a NOT gate. Okay, that's one multiplexer. So multiplexer. This is your block, right? Say this is a 2-to-1 MUX, 2 input with one selector and 1 output. Okay, so basically selector is also a part of your input, right? So it's S, A, G. Okay, so these are the states, okay, the conditions. You've got 3 variables, 3 input. Thus you will have all these 8 conditions, and these are your output, okay, your marks. All right, so this is the circuit that you get from the Y, right? Okay, this is just an overview before we go into marks. Okay, 21 marks. Right, the multiplexer has a number of data inputs. Okay, data inputs is here, your data inputs. Here is W0 and W1. And you've got 1 or more select inputs and 1 output. Okay, it's always 1 output. Okay? It passes a signal value on one of the data inputs to the output. Data input is selected by the values of the select inputs. So here you've got a truth table. S is your select. So if S is 0, your F will be equals to W0. While S is 1, if S is 1, F will be equals to W1. Okay? So select into S chooses as the output of the MUX either input W0 or W1. This is a circuit that you get, okay, from your truth table. Your SOP circuit here. You get from your truth table, your SOP circuit. And another way to draw your circuit is using these transmission lines. Okay, not just an information. Okay, you don't have to worry about that at this point in time, but just worry about, just know that this is your MUX, 2-to-1 MUX. Okay, be familiar with it. Okay, you've got this you've got 2 AND gates. Okay, 2 AND gates. One OR gate and 1 NOT gate. Okay, so that's 2-to-1. Okay, so again, this is your truth table. Okay, for the 2-to-1 MUX. Okay, again, you have 2 inputs, X and Y, X1 and X2. Sorry, X1 and X2. 2 inputs. You've got a selector line, a select line S. So if S is 0, F will be equal to X1. If S is 1, F will be equal to X2. Okay, so this is your expression. Let's derive it now. Alright, having derived this expression, you'll see how we can get this. Right? Let's derive it. So from the SOP, from this truth table, you get where you derive the SOP form, whereby when the output is 1, so that is your Asian signals in there. Where is my Asian sign? So it's S bar, X1, X2 bar, S bar, X1, X2, S X1 bar, X2, S X1, X2. Okay, so this is when you have 1 at the output. From there, you get your SOP. So this is your SOP form, but you're not there yet. You can simplify it. Okay, so simplify using your Boolean laws. Okay, you have your simplest expression there. Alright. So from here, that's how you can get your circuit. Alright. I'm not going to go through that. I'm sure you know how to. From an SOP equation, from an SOP expression, you can find your circuit. Now let's look at this analysis. Okay. So when the input S is 0, okay, when input S is 0, you have this a NOT gate there. Thus at the first AND gate you've got a 1 and X1, but for the second AND gate you have a 0 and X2. Okay, so if you know from the AND truth table, when you have a 1, then only the output will follow the input, right? Yeah, when one of the gates is when one of the terminals is 1, the output will follow the input here. So here is F X1, here output here is 0. Okay, and yeah, okay, so F equals X1. So this is when S equals 0. Okay, S equals 0, F equals X1. When S equals 1, okay, you have F equals X2. Alright, because here you've got a NOT gate, you've got 0, 0, 0, X1, 0 is 0, and here you've got 1, X2, you've got X2. Right, and you OR them, you have your F. Okay? This is another way to draw it. Okay, your block abstraction. Okay? You have this when S is 0, F equals X1, when S is 1, F equals X2. So that is 2 to 1 marks. Okay, remember this. Remember this. Alright? 4 to 1 marks. 4 to 1 marks. Okay. This is your graphical symbol. Okay, 4 inputs. Since you've got 4 inputs, therefore you've got 2 select lines, right? 2 from 2, which is 4, right? So it's always the power of 2. Okay, and this is your truth table, S1 and S0. So here, S1 and S0, you've got two inputs, so 4 conditions. So F equals W0 when S1, S0 is 0, F equals W1 when S1 is 1, S1 is 0, S0 is 1, and so on. Okay, I'm sure you guys know this already, right? Yes. Okay, so this is your 4 to 1 marks. Okay. From here, if you were to do your, this is a simplified. From here, from this truth table, you can get an expression here. Okay, your SOP expression. So here you've got this omega. Sorry, W0 is when S1 and S0 is complete barred. Okay. Complemented. And here W1 is when S1 is complemented and S0 is true. Okay? And here W2 is when S0 is complemented and S1 is true. And here W3 is when S1 and S0 is not complemented. Okay? This is true values. So this is your expression you can get from this truth table. From there you can build your circuit. Okay? Right, let's look at some analysis. When S0 is S0 0, S1 0, you have having this NOT gate, it makes this to 1, 1. So thus you have omega 0, W0 at the output of the AND that will reach to the F. Okay? Alright, W0. So when S0 is 1, S1 is 0, you have the F to be W1. When S0 is 0, S is 1, you have F to be W2. When S0 and S1 are both 1s, you have F equals W3. Okay, and this is the block diagram on the graphical symbol. Yep, this. Okay, so this is your multiplexer. Okay, continue. So we are able to build larger marks using the same approach. Usually the number of data inputs n is an integer power of 2. Larger marks can also be constructed from smaller marks. Example, you can construct a 4 to 1 marks using 3 2 to 1 marks. And you can also construct 16 to 1 marks using 5 4 to 1 marks, right? So let's look how we can do that one by one. 4 to 1 marks using 2 to 1 marks. Okay. So here, remember this picture just now? Okay, I've been telling you guys, this is the 2 to 1 marks circle. Okay, 2 to 1 marks circle, right? So I'm going to build a 4 to 1 marks using my 2 to 1 marks. So I need 3 of them in order to build 4 to 1 marks. Okay. So I join and connect the 3 marks together. Okay. Here I've got here, so you can see my S1 here. Okay. So S0 here is a select for this marks and this marks. Okay. While S1 here is the select line for this marks. Right. So each mark which needs one select line. Okay. Alright, so this is a 4 to 1 marks. Okay, so this is different from the SOP form or the 4 to 1 marks video, which uses fewer days. Okay. So this is a showing graphical. Okay, so remember this is the picture I showed you just now. Okay. Okay. So here you've got this when S1 is 0, S0 is 0, you have F equals W0. Okay. So when S1 is 0, S0 is 1, you've got F equals W1, and so on. Right? Alright, so that's 4 to 1 marks. What we want to show before that, I showed you this is one way to draw your 4 to 1 marks. Okay? Another way is, as I showed you just now, using 3 of 2 to 1 marks. Okay? So there are many ways to draw your digital circuits. Okay? It's up to you whether you want a simpler design or a faster design. Okay, sometimes faster design will need more complexity, need more wires and so on. But if you have a faster design, you would have usually you would have less gates. Okay. All right, 16 to 1 marks. 16 to 1 marks. You have this 16 data inputs. Okay. We've got 4 select. Okay, 4, 2 to 4. Right, so we've got 4 select lines. Okay, so those are showing you here. When it's S1, S0, you have this W. Yeah, what this comes out, but you need also the S3 and S2 to figure out what F is here at the end. So when all this 1, 0, 0, 0 as your select lines, okay, what you get F is W3, right? And so on. Okay? So this is a 16 to 1 marks. Whereby you need 4 select lines and you've got 16 data inputs here. Alright, synthesis of logic functions using marks. Okay, so here, marks are useful in many practical applications. Marks can also be used in a more general way to synthesize logic functions. Consider the example whereby you have a 4 to 1 marks. You can make this more simpler, okay, by changing this into a 2 to 1 marks. Okay, let's look at it one by one. This is a 4 to 1 marks. Okay, 4 to 1, you've got 2 input lines and 2 select lines. Okay, and 4 data input. Okay, so the truth table here, if you look at the truth table here, it shows the functions of F equals W1 XOR with W2. Okay, so again, XOR is much used in digital systems, digital circuits. Okay, so F equals, in this marks truth table, F equals W1 XOR with W2. You see, there's a truth table of an XOR. So this function can be implemented by 4 to 1 marks. So basically, you can use the marks to implement your XOR function. Values of F in each row of the truth table are connected as constants to the multiplexer data inputs. The mark select inputs are driven by W1 and W2. Each valuation of W1 and W2 F is equals to the function value in the corresponding row of truth table. Now we can make this 4 to 1 marks into a 2 to 1 marks by you grouping this into 2's, right? So here you've got when W1 is 0, F equals follows W2. But when W1 is 1, F is equal to the complement of W2. Alright, so we are grouping this in two groups, okay, and making it into a 2-to-1 marks. Okay, this is a 2-to-1 marks circle. Okay, this trapezium is always showing marks. It's a symbol for marks. Okay, of course you need a NOT gate there in order to complement your W2. Okay, so this is a 2-to-1 marks. One of the input signal W1 in this example is chosen as a select. So here you've got a select input of W1, you call it. Okay, so you select input 1, when W1 is 0, F equals that. When W1 is 1, F equals the complement of W1, no, W2. Right, so that is, I'm using a mux as an to show an XOR. Like if I can also use a mux to show an AND, an OR, and a NOT. Okay, so here I'm building an AND gate using a 4-to-1 mux. Okay, so here you see this is the truth table for an AND gate. Okay, for an AND gate. So you see this is the mux. Okay, so I'm putting the inputs as shown here. Okay, and say for x1 and x2. Okay, I've got 2 inputs, therefore I've got 4 conditions. Okay. Alright, so this is how I would show how I use my mux as an AND gate. Here I'm using 4-to-1 mux as an OR gate. Okay, so just I apply the output of an OR gate onto the mux. Okay, so these two are the same. So this 2. Okay, so from there I can use the 4-to-1 mux as an OR. Here I can also use the 4-to-1 mux as a NOT gate. So what I do is I need to introduce the dummy variable y. Okay, there you go. Now set y to either 0 or 1, or both will work. So you've got 2 alternatives. So I put the y as a 0 or a 1, but I can still get my x to be complemented. Okay, so I can still build a NOT gate using a 4-to-1 mux. Okay, that is using 4-to-1 mux. Here I'm building AND OR and NOT gate using a 2-to-1 mux. Okay, same thing. Okay, what I can do is I group it into 2 groups here, just as I did just now. Okay, for the 4-to-1 mux, from the 4-to-1 mux table, we group it into 2s in order to implement this into a 2-to-1 mux. Right, so here when x1 is 0, so you have x1 and x2 are 0, but when x1 is 1, you've got x1 and x2 is equal to x2. Okay, so this is how I build AND gate using a 2-to-1 mux. Here I'm building an OR gate using a 2-to-1 mux, same thing. I group it into 2s. Okay, so here when x1 is 0 as my select line, now x1 is my select line. x1 is 0, I've got the output to be following x2. When x1 is 1, the output follows x2. The output is 1. Okay, the method. Alright, so this is OR gate. Now I'm building a NOT gate. Okay, same thing here. Okay, more simpler. Now, so this is my AND. So again, what is this? This is a 2-to-1 mux circuit. Remember, why am I always saying that? I don't know. Okay. So yeah, this is a 2-to-1 mux circuit. I'm using 2-to-1 mux to build my AND or a NOT. Okay. Alright. Okay, done that. Now I'm building XOR gate with the 4-to-1 mux. Okay. Now, look at this. Example, 2 switches that control the light. We've gone through it in the first class, I think, using an XOR logic gate. Okay, from there you have a truth table. This is my XOR function. Okay, and from here you have the logic network. Okay, this if you remember is my 2-to-1 mux, but added with the NOT gate there. Okay, makes it into an XOR logic gate. Alright, so here I'm using I'm implementing an XOR with a 2-to-1 mux. So this is my XOR truth table. Since we are having a 2-to-1 mux, I'm grouping it into 2s. W1 is my select line. So here F equals W2. F is W2. F follows W2 when W1 is 0, and F follows W2 complemented when W1 is 1. So this is my circuit just now as I showed. Well, this is the circuit from here. Okay. So here I put a NOT gate because I need to complement the W2. Alright, so here is when you use another NOT gate, right? Why am I using a another NOT gate because as I showed you just now, I need to complement the each of the X and Y, right? Okay. In other words, all these four are equivalent. We've got this XOR logic gate, and from here, this is my circuit using a 2-to-1 mux with a NOT gate, additional NOT gate. This is a graphical symbol, okay, of the XOR gate using a 2-to-1 mux, and this is a 4-to-1 mux, okay, that can implement an XOR gate. Okay, remember? Can you remember? Can I put this in the text? Okay. Now, example: 3-input XOR using 2-to-1 mux. Okay. So here we've got 3-input XOR, W1, W2, W3. This is much used if you remember in the full adder. Okay, for the sum, it's A XOR with B XOR with the Cin, right? So this function is quite useful. So if you are to draw or design a full adder, we need this 3-input XOR. Alright, so 3-input XOR can be implemented using 2-to-1 mux. Okay, 2-to-1 mux. When W1 equals 0, F equals to the XOR of W2 and W3. This is my truth table. You can see that here when W1 is 0, W1 is 0, F follows. F is actually W2 XOR with W3, while W1 is 1. F is the XNOR of W2 and W3. Okay, so XNOR. So the left multiplexer in the circuit produces W2 XOR W3, while this one it XOR the output of this. Okay, so this is what you want: 3-input XOR W1 XOR W2 XOR W3. At this node here, at this interval node here, you've got W1, W2 XOR W3, and then you XOR it again with W1. That is your F. Alright, so this is again how I did this now. Okay. But now I'm using a 2-to-1 here. Right, 2-to-1 mux. Okay, another way to look at it. Okay. So here you've got this is W3, following W3, and this is following W3 bar. Okay. And implementation of XOR with the 4-to-1 mux. Okay. So what you do, you group it into twos. Okay, four groups of twos. Okay, you see that. Okay, this one because remember for the 4-to-1 mux, you need two select lines, which is your W1 and W2. Okay, so these are your select lines, and for that you have your F. Okay, F which follows W3 accordingly. Alright? You just need to remember this. Alright? Well, you don't have to remember once you draw your truth table and know what you want to use, 4-to-1 mux or 2-to-1 mux. From there, you can figure out how you can come up with a circuit. As long as you have your truth table, you're fine. Okay. Alright. Another way I'm showing you here, the application of the multiplexer is a 2x2 crossbar switch. Okay. So a circuit has two inputs x1 and x2 and two outputs y1 and y2. When there are two inputs and two outputs, it's called a 2x2 crossbar. Okay, 2x2 crossbar. So the mux select inputs are controlled by signal S. So you've got for 2x2 crossbar, you've got one select line which is S. So if S is 0, the crossbar connects x1 to y1 and x2 to y2. But if S equals 1, the crossbar connects x1 to y2 and x2 to y1. This is called the crossbar switch, right? And this is the circuitry, right? This is a demonstration of it. Okay, so when S is 0, we've got x1 equals y1 and so on. But when S equals 1, it's crosses. Yeah. All right. So this is implementation of the 2x2 crossbar with mux. All right. Okay. And now I'm using again. I keep showing this, keep popping up, right? This 2-to-1 mux circuitry. Okay, it keep popping up. So I'm implementing this tool in a 2x2 crossbar switch, right? So you have this connection as shown here. Okay. Now I'm giving you another example: 3-input majority function. Okay. So this figure shows the truth table for a 3-input majority function. That means when you have a majority of 1, you put a 1 there. Okay. When the majority is 1, you put a 1. Majority of 1, you put a 1. Majority of 1, you put a 1. When there's more zeros, you put a 0. So that is the truth table for the majority function. Modify the truth table to implement the function using 4 to 1 marks. So I'm modifying it to become like this because I want to use the 4 to 1 marks. Okay? Any two of the three inputs may be chosen as the marks select inputs. Okay, any two of the three. So, okay, you need 4 to 1 marks, therefore you need two select inputs. So here I'm using W1 and W2 as my select inputs. Okay, so my F will be in terms of W3. Okay, another implementation is shown here. Alright, so all this time, that's why I show you here, because this is keep being used. Okay, the 2 to 1 mark circuit. Okay, it's copied. Alright, now, mark synthesis, almost there, almost finished it. Okay, so I like to do this kind of context. Okay, we're almost finishing, you guys. Mark synthesis using Shannon's expansion. Have you guys learned about Shannon's expansion? Have you guys heard of it? In communication system? No? Communication what? Communication something. Alright. Tables can be interpreted to implement logic functions using marks. In each case, inputs to the marks are constant 0 or 1 or some variable or its complement. It can be W3, W3 bar, so that's your input data. Besides using such simple inputs, it is possible to connect more complex circuits. So instead of having 1, 0 or W3 or W3 bar, you would have input from another circuit. Okay? So that can be happened also, allowing functions to be synthesized using a combination of marks and other logic gates. Okay, so we're using Shannon's expansion for this. Okay? Suppose that we want to implement a 3-input majority function as we did just now. Okay, 3-input majority function using a 2 to 1 marks. Okay, if we want to use a 2 to 1 marks. Okay, so here, where do I get this expression? This is my 3-input majority function here. Okay, so we've got this. If you look at this one, where is the SOP expression. So when W1 bar, W2, W3, okay, W1 bar, W2, W3, or with W1, W2 bar, W3, W1, W2 bar, W3, or with W1, W2, W3 bar, W1, W2, W3 bar, or with W1, W2, W3. Okay, so this is from your SOP function of this third 3-input majority function. And then what you do next is you simplify it, you factor out W1 out of this, you have this expression here. Okay, W1 bar, W2, W3, or with W1, W2, W2 bar, W3, and so on. Okay, and from here also you can find that, okay, this is the same as this. You can even simplify it. Okay, simplify it using a Boolean identity. Okay, you can simplify this to become this, right? How do I get? Go back to your Boolean identity to get from this point to this point. Okay. Anyways, I want you guys to focus on this line here. Right? Here you've got W1 bar, W2, W3 plus W1 without a bar, W2 plus W3. Okay. This is a kind of a Shannon expression. Okay, Shannon expansion expression. Okay. All right. So going next. So this is when I say, but this term, this function is ended with W1 bar, and this another expression ended with W1 true, okay, without the complement. Okay, so this is like a Shannon form, a Shannon's expression form. All right. So you see here, you see this is any Boolean expression as I showed. This is an example of a Boolean expression, right? So any Boolean expression, you can go to this kind of form. You can do it in terms of this form. One with a bar and one without. Okay? So any Boolean function can be written in the form of this, whereby you have a function equals, say you've got a function with in terms of W1, W2 until Wn, equals W1 bar. So I take out, for Shannon expression, I take out the factor of W1, say. I can take out W2, I can take out W1, whatever. but in this example here, I'm taking out W1. So here W1 bar ANDed with a function whereby the W1 inside that function is 0, okay, where W1 is 0, or with another term in that expansion where W1 is 1. Okay, here W1 is 1. Alright? Okay, so what are we talking about here? Actually, this is like the 4 to 1 marks I showed you before. Okay, 4 to 1 marks. Okay, say that I have a 4 to 1 marks with a function there, right? So 4 to 1 and 1. Okay, so here this is W1, W2, W3, W4. It's not good. Okay, let's say W0, 1, 2, 3, 4, but 0, 1, 2, 3, but say I put W1, W2, W3, W4. Say that. Okay, as I showed in this function there, right? I've got W1, W1, and so on. Okay, so from this, so here's the pattern, right? So this is like a 4 to 1 marks. Okay, so for Shannon expansion, we just say that how I can use this 4 to 1 marks, okay, to build something like a Shannon expansion there. Okay, what I'm saying, I'm using this again. Okay, I'm using this again. So here is my F. 1, 2, 3, 4. Another. And 1, 2, 3, 4. Okay, say I'm not going to put a W1 there. Instead of a W1, I put a 0. Okay? And instead of W1, I put a 1 here. Here, W2, W3, W4. W2, W3, W4. Okay? Because here, I gave you here, when you have a Shannon expansion, you've got one is W1, which is 0. Here, W1 is 1. Right? Now, I'm going to use I'm going to make this into a Shannon expansion that can reflect this. Okay? Alright. So here, what we have is and there's an AND gate here, AND gate there, 2 into AND gate that goes out into an OR. Because here I've got an OR expression here, right? Okay, so got an OR there. Okay, so that's my F. Okay, here for this one it can be W1 bar or W, right? So this can be W1 bar, W1 bar. On this one is W. Okay. Okay. So W is 1. Okay, or I can say W1 I show here, and this is an AND gate, not gate, and this is my W1. So W1, W1. Okay. So what I did just now is I'm using this marks, 4 to 1 marks, to draw a Shannon expansion circle. Right? Shannon expansion circle. What is Shannon expansion? Shannon, you can use from any Boolean expression. You can simplify it by using Shannon expansions. Okay? So what is Shannon expansion? It's a form of where you can factor out whichever variables out. Okay, here you can factor out W1. So factor out, take out W1. So one term is W1 bar, one term is W1. So this is the circle. Okay? Can you draw the circle? Yeah, this is the circle. Alright? So in Shannon expansion, the term, what this term means is when W1 in the equation, in the expression when W1 is 0, okay, you have to include W1 is 0 for this one. Okay, for this one, where you have to include W1 is 1. I'm going to show an example in one. Okay, just first now it's just definition. Okay, so here this definition is equals to this. The same thing. F, okay, F in terms of W1, W2, whatever, equals W1 bar and this whole function whereby W1 is complemented, or with W1 ANDed with the function where W1 is equals to 1. So this is called a cofactor and this is called a cofactor. Right? So example, I'm using a Shannon expression for 2 to 1. Okay, let's look at the 2 to 1. Assume that we wish to implement the function this. Okay? This function there. It's a different function from just now. Okay? It's a different function from here. Okay? Okay, say that we want to implement this function there. using a 2-to-1 mux and add any other necessary gates. Okay, Shannon expansion using W1, meaning W1 I'm factoring it out. So here F equals, so this is your Shannon expansion as now, Shannon expansion, whereby W1 bar with the function where W1 is bar, or with W1 where the added with the W1 is equals to 1. So what you do is, from this expression here, okay, this is when you apply W1 equals 0, okay, so here you can cancel off, here you can cancel off, so here is what you are left with, right, W3, right, W3 bar, okay? So this is when you apply W1 for 0. Now, when W1, for this term here, for this cofactor, where this term means W1 equals 1, you are left with this one. You're left with W2 plus W1 and or with W3. Okay, so from this, you can build your circuit. Okay, 2-to-1 mux. Okay, here you've got your W1. Here is your select lines. When I take out, when I factor out my W1, that means I'm selecting my W1 as my select line. I'm choosing my W1 as my select line. So W1 is my select line here. Okay, and then you've got W3 bar into the mux, and then here I've got W2 or with W3 into the second input of the mux. So what am I doing? Instead of having a mux that has a data line of a variable or a bit number 0 or 1, instead of that, I have a circuitry that goes into the mux, right? So I'm using Shannon expansion to build this circuitry, right? Where does this circuitry comes from? From this complicated equation there, from this complicated Boolean expression here. Okay? Alright? Okay, again, okay. You are given this Boolean expression. Okay? Is it complicated? So lah. Okay? It's not that complicated. Anyway, it's a Boolean expression. From this Boolean expression, I use Shannon expansion. Okay, you use Shannon expansion when you want to use a mux. Okay? Okay, the Shannon expansion allows us to choose which we want to use as our select line. Here I want to use W1 as my select line. Therefore, I take out W1. Okay, and the rest is my cofactor. Right? So I take out W1 and the rest will be my cofactor. Now, the first term is when W1 is 0, and the second term is when W1 is 1. So here, when W1 is 0, this one will cancel out. We'll just leave my W3 bar, so W3 bar, or with, now when W1 is 1. So W1 is 1, it just leaves me with these two terms. Okay, this one will be cancelled off. Okay, so W1 is 1, is W2 or with W3. Right? So now I've got a more simpler circuit that I can use, whereby W1 is my select line. Okay, so now W1 is my select line. I can set what are my data inputs. Right? So this is for a 2-to-1 mux. Let's use a 4-to-1 mux. Okay, let's use a 4-to-1 mux. Okay, so using this expression. Okay. Okay, yeah, using this from this purple box, same, from the purple box there, from this purple box, I want to use Shannon expansion. Set Shannon expansion, but if I have a 4-to-1 mux, I need 2 select lines, right? For 2-to-1 mux, I just need 1 select line, but 4-to-1 mux, I need 2 select lines. Now, in this slide here, I'm using W1 and W2 as my select lines. Okay, so take this out. Okay, so you've got a bar, both bars, okay, and then you've got cofactor, or with when only one of the select lines are barred, cofactor, and when again one of the select lines are barred, your cofactor, and here when both are not barred, and your cofactor, right? And here you've got when, so basically you include, okay, you put in when W3, here when, from here, okay, from here when W1 and W2 is equal to 0, you're only left with this W3, okay, W3, and from here when W1 is 0, W2 is 1, you have this, again, you have only this term. When W1 is 1, W2 is 0, you have this term only, and when we have both, sorry, this when both are ones. When both are ones, you have only one. Okay, this one. Okay, so you say it's one. Okay, so from there, I don't think I need to draw on the board because it's written here. Okay, so I don't think I need extra things. No, it's actually I've drawn it already, so I don't have to draw on the board. So this is the result. Okay, so you've got two select lines, W2 and W1. Here you've got W3 bar as the first data line, and then the second data line is when it's one. When W3 bar again, W3 bar, and here is W3, and here the last data line is one. So that's your Shannon extension. Okay, let's look at another example. This is using three-input majority function. Okay, so another example. Look at the black, purple in the purple box. Okay, you've got your equation, your Boolean equation. Use your Shannon expansion so that you can set your 2 to 1 marks. So again, 2 to 1 marks, it just needs one select line. So I'm choosing W1 as my select line. So W1, this is when the W1 term is 0. So you've got 0 and it with W2 plus 0 and it with W3 plus W2 W3. So that just leaves with W2 W3. Okay. Then plus W1. So when W1 is 1. So W1 is 1 times W2 or with 1 and it with W3 or with W2 and W3. So that just leaves me with this term here. So thus, for this function, I have this function to apply into my 2 to 1 marks. Here I use the G and H as my, okay, I denote it as a G and H. Okay. Does it have anything to do with the full letter? Maybe. It's more or less the same term. Okay. Shannon expansion again. Okay, you can make more Shannon expansion out of that. Okay, and you can make it even into a 4 to 1. 4 to 1 marks. Alright? Okay. Okay, so now that is done for the, I think, the hard part of the lecture today. Right? Not hard, a bit understanding. Okay. The next is the standard MSI. So this is just some standard chips, okay, that you can get commercially off the shelf. Okay, the 74151A. Here you've got this chip is the 81 marks with in low asserted input enable, okay, whereby it's triggered when it's low. Okay, are you guys talking about any questions? Questions? No. Okay, so let's start some chips. Right, any question, please answer. Please question. Please ask. Okay? Please ask. Don't wait. Don't wait until it's 14. Alright, decoder. Again, you've done this before, so I just go through very quickly. And to do what to from n decoder is a multiple output combination, 2 input lines from n output lines. Okay, so this is this circuit. Okay, it has it's a 2 to the decoder. It's a decoder, binary decoder, right? So you've got what to decode 0 0, that is 1, 0 1 for y1, 1 0 which is y2, 1 1 which is y3. Okay, so we can also call it as a one hot encoder. Okay, another term for it. Okay, so this is the 2 to 4 decoder. Okay. Right? Okay, 2 to 4 decoder when W1, W0 is 1, W1 is 0. You triple it into this circuit, you have Y1 as 1. Okay? Alright, adding an enable input. Okay, enable when it's only 1. Only when enable is 1, you only will this circuit works, but if it's 0, it doesn't work. Alright, so this is a binary decoder with enable. So when enable is 0, we don't care what W1 W0 is. Only when it's 1, then only the output follows what they need. Okay? Alright. How we can build larger decoders? Some needs 3 to 8, 4 to 16, or 5 to something. Right? So here you have a 3 to 8 decoder using 2 to 4 decoders. Okay. What is this? This is not a 2 input mux. Okay? This is called a 1 to 2 decoder. Okay, this is a 1 to 2 decoder with enable input. Okay, this part of the circuitry here. Alright, 3 to 8 decoder is in 2 to 4 decoders. Okay, if you see here, when it's enable 0, nothing comes up, but when enable is 1, you're enabling the circuit. So when it's 0, 0, 0, you have Y naught, D naught to be 1, Y naught to be 1, and so on. Okay, when 0, 1, 0, 0, 1, 0, you have Y2 or D2 to be triggered. Okay, and so on. Okay, here you've got the 4 to 16 decoder being built using a decoder tree. Okay, that is using 2 to 4 decoder to construct a 4 to 16 decoder. It has a tree-like structure, that's why we call it as a decoder tree. Okay, decoders to build mux. See, I see you guys tired already, right? Only 1 hour. Okay, so never mind, very quickly, right? Decoder, 4 to 1 mux built using a 2 to 4 decoder. 2 to 4 decoder. Okay, you are building a mux. Okay. Alright, so this is from the truth table, you can get this SOP expression. Now Dmux. Dmux is the opposite of a mux, right? So you've got one input and you've got multiple outputs. Okay, so that's Dmux. Instead of an enable, you have a data line. Okay, and of course, same as a mux, you have a select line and 4 output lines. Okay, so this is your circuitry. Okay, so you've got data line 1. Okay, so 0, 0. That Y naught will be equal to the data input. Okay, when it's 0. Okay, when you have a 0 at the data, you put 0 everywhere. Okay, here. Okay, so here when it's 1, 0, this data line will be sent to Y1 and so on. Okay, when it's 1, 0 or 1, 1 and 1, 1, this data line will be sent to Y3. Alright, so a bit more. Encoders. I've got 2 examples, priority encoders and code converters. Okay, so encoders perform an opposite function of a decoder. It encodes input information into a more compact form. Decoder is a combination logic that assigns a unique output code for each input signal, opposite of a decoder. Okay, so binary encoder. Okay, so this so here you've got W naught. Okay, so it's 0, 0. W1, that means it's Y1, 0, Y naught is 1. W2 is 1, that means Y1 is 1, Y2 0. W3 is 1, both Y1 and Y naught is 1. So I'm using a 4 to 1 binary encoder. You see here, okay, again, the third 1 port encoded. Now here, this is my circuit. You see that it's floating here. W naught is floating. Why is that so? I need this because I want to use a 4 to 2 binary encoder. So I have to include the W naught, but you cannot keep it floating. You need to add a number. You need to assert a number onto it. Okay, either 1 or a 0. Okay. So when it's 0, 0, 1, 0, you have an output of 0, 1. When you have 0, 0, 0, 1, you've got an output of 1, 1. Alright, so these are the expression for the 4 to 2 binary encoder that I showed you just now. Okay, for this truth table, this is actually an abbreviated or a simplified truth table. This is the longer version of the truth table, but I do not need the other parts because we just want to find where there are multiple inputs set to 1. I'm not showing you the truth table. So for example, you've got 2 1s there, you don't use it as a binary encoder, so I say it's a don't care. So when you've got multiple sets of 1s, the output is a don't care. And that's why it's not shown in the abbreviated truth table. Alright, so how do I get the circuit? You just use an K-map, you can get the SOP function, you can get the circuit. Alright, next is priority encoders. Priority encoders, when in a priority encoder, each input has a priority level associated with it. The encoder outputs will indicate the active input that has the highest priority. I believe you guys have done priority encoder in digital systems. Yes, right? When you have when the MSB the most significant bit is 1. Okay, most significant bit is 1. So for example, here, right? Here you've got this okay, let me show you. Okay, let's look at the demonstration. Okay, so when it's 0, 0, 0, okay, you've got 0, 0, 0, 0, 1 here. Okay, that is where z is 1. 0, 0, 0, 1 x, we don't care. Okay, we don't care what is the w0 because w1 is the most significant bit with the 1. Right? W1 is the most significant bit with the 1, so we don't care what w0 is. So y0 is 1. Right? And then here, for example, when the w2 is 1, we don't care what w1 and w0 is. Okay? So the y1 is y1 and y0 is always 1, 0. And here, when the w3 is 1, we don't care what w2, w1 and w0 is. The MSB is already 1. So that is a criteria. From there, you get your SOP circuit, SOP functions and SOP circuit. Okay, next, code converter. Code converter, yeah, this one I think you will be using for your labs. Okay, when you do your 7-segment display. Okay. So here it just shows. So for this one, this is C because this is a hex. Hex 7, yes, hex. So this is C in hex. It changes to show in the 7-segment display C. Right, and so on. This is a 4, so it shows this LED will light up. Okay, so you'll be using this in your understanding in your labs, I believe. Okay. All right, another example. Show how the function this with the mean terms of 0, 1, 3, 4, 6, 7 can be implemented in 3 to 8 binary encoder. So this is how we do it. You've done it before, I think, digital systems, right? So we just get an OR gate to work everything out. That's, yeah. Next, implement an 8 to 3 binary encoder. 8 to 3 binary encoder. Okay. So 8 bits input to a 3 output. Okay. So here is your, so you get your SOP for Y0, Y1, and Y2. From there, you can get your circuit. Okay. You've done this before, I believe. This exercise in which how to draw a circuit from the truth table, get your SOPs, expression as this, and thus you can get your circuit. Alright? This is another 8 to 3 priority encoder. Get your truth table right. From there, you can get your SOP. From SOP, and you can get your circuit. Okay? Alright. Another example. Implement the functions using a 4 to 1 max. Okay. Okay, from this function, you can reduce it as shown here. Okay. And from there, you can see my W1 and W4 is my select lines. Okay. So W1 and W4 are my select lines. And yeah, from there you can get your 0, 0, 0, 1, 0, 1, 1. How do I get this? You guys, please, a bit more, please. Okay, quiet down, please. Quiet down. Okay, quiet down. I'm very really disappointed in you guys. It's not 10 o'clock yet. Okay, this one. So this is your, okay, W1 and W4 is my select lines. Okay, from here is my data input for the one. Okay, data input for my 1, 0. Okay, data inputs for my 0, 1, and data input for my 0, 0. Okay, yeah, actually it's from this expression here. Okay, so as again, for your marks, sometimes you don't just have to, you don't have a particular bit or a variable like like one variable only. It may have, you may be given a function, and from there I would ask to implement this function onto a 4 to 1 marks. Okay, so when I say I, that means I'm talking about your test or your exam. Okay. Alright, Verilog for combination circuits. This one, you guys have a look at it. I don't know where are you guys with at your Verilog exercise. Please, before, it is very good to, I've given you the link so that you can try the link to practice your Verilog at your own time. It's very useful. So you can have a look at these examples as you go along. Okay? Alright, done. Okay? So again, your test will be on week 7, another 2 weeks. Okay, another 2 weeks. On Wednesday at the exam building. Okay? 10 o'clock. Who cannot make it at 10 o'clock? Because it will be 10 to 11. Who cannot make it from 10 to 11? Maybe a simultaneous group 1 and group 2 will have the same time. No. No, I've got a Raya party at 11. So you have to start. Okay lah, dah jadi. Okay? But we need to finish at 11:30. Okay? My Raya party starts at 11. If I go late, then my food finishes.